Good afternoon. I'm Jae Park from Seoul National University, South Korea. I would like to present today system integration of our robot TOCABI, torque-controlled biped robot, which is developed in our lab. The specification of TOCABI is the following. It is an adult-sized humanoid robot. Its height is 180 centimeter. The weight is 100 kilogram. And it has many degrees of freedom. Each arm has 8 DOF. The waist has 3 DOF. The neck has 2 joints, and each leg has 6 joints. It is featured with anthropomorphic design with a wide upper body workspace. This is mainly due to the 8 degrees of freedom of each arm. Because of this degree of freedom, we can move a bit like a human upper body, and it has a larger workspace. And we can do torque control on the joint of the robot via current controller on the motor drivers. And each actuator module consists of electric motors with harmonic gears. And system integration is based upon ROS, and we use Ethercat communications. If you look at our robot, it has, as I mentioned, 180 centimeter. So in the middle of the picture, this is Jae Shin in our lab. His height is 180 centimeter and weight is similar to the robot. And you can see on the sagittal view, the robot's back is quite a bit similar to human. And you can see the pelvis and the arm. So we have tried to mimic or design it to be a little bit similar to human overall. And this is some of the performance of our robot TOCABI in gravity compensation. So you can see that the robot is standing still, standing on 2 feet, and a person can move around compliantly. So because this is only in gravity compensation mode, you can move the robot and robot will stop at certain position. And this is also due to the friction we have a little bit. If there's no friction, then robot can move wherever, but we can stop the robot with a little bit of friction, and then we can adjust the posture as we want. And another feature is here that you can see that this is very similar to gravity compensation mode. So only on the lower body we have gravity compensation. Upper body is controlled to maintain the posture, and COM is all bit controlled on the lower body. So you can see that with the disturbance, external disturbance, we can move the position and orientation of the foot. However, the robot can maintain its balance and doing gravity compensation without that much of a problem compliantly. So here we are using IMU sensor for the roll and pitch, but we don't use FT sensor in this case. And this is a similar performance as before. We can move the feet, orientation and position, but still we can have compliant motion on the lower body with the gravity compensation on the lower body. So this is quite important feature for our robot. Through the torque control capability, we can have this compliant motion. All the more detailed specification is the following. So general specification was presented earlier, and robot control unit has a PC with i7 CPU, and operating system is based upon Linux, Ubuntu, and real-time performance is using kernel Xenomai. And Ethercat master is selected as simple open Ethernet master lesser program, so it's SOOEM. And data acquisition card is Sensory 826. And motors are two different sets. One is Komogen series for the lower body, and Parker K is for the upper body. And Elmo Gold Solo Whistle is used for all the controllers, all the drivers for the motors, Komogen and Parker. And we are using magnetic encoder and harmonic gear, and all of them is 100:1. Actually, originally we chose to use 50:1, but we needed more power, so we changed it to 100:1. We are using homing sensor, and as I mentioned, we have IMU, which is used to determine the orientation in space, and full stroke sensor is not actively used, but we are using mostly to measure how much force strokes are applied on the feet. And this is how the main PC is connected with the sensors and actuators. So you can see that yellow is analog connection here from FT sensor to DAQ board, and green is PCIe communication, and blue is USB, and main control PC is communicating with motor drivers through two parallel channels. And wireless communication is to connected to the remote control PC for GUI, graphical user interface, and commands. And these are some of the illustration of hardware features of hardware components of TOCABI. And there can be actually probably three popular choices of communication interface: CAN, RS485, and EtherCAT. And we chose to use EtherCAT communication. And here you can see that transmission rate are different depending on which one to use. From CAN RS485 to EtherCAT is getting a more larger transmission rate in general. And these are all daisy chain field bus topologies. So if I explain it a little bit further here, so EtherCAT field bus technology is known to have high bandwidth with lower loss. And this communication software is very important to implement the real-time controller and to have a robust control performance of the robot. So this is how we implement it in general. So T is transmit and R is receive. So here in thread 1, you can see the communication is going on here and there, and in between, in the second thread, we update robot state from communication, and we check the robot state, and we go through state machine what to do, and simple planning here, and control the robot. We send data to GUI and data log, and these are in the second thread. And the third thread is not real time, and we can have a little bit longer planning. So thread 1 and thread 2 is supposed to be in real time, and thread 3 is non-real time thread. So the division of the programs can be seen here on the left, a little bit more in detail. And you can see a little bit of a bigger picture here, that you can see that above GUI is the real time, and in the lower part, GUI parallel program for complex computation, different sync programs are in the non-real time thread. So this is the overall architecture of our software framework. And real-time OS is quite important. Probably many of you already knows, but if I emphasize all of it, more, real-time OS does not mean high or fast computing performance system. It is a bit of scheduled system that the real-time OS can guarantee the scheduling of the programs. So if they say that we can finish in like 0.01 millisecond for certain tasks, then they can guarantee, the OS can guarantee this scheduling. So this is most important part of the real-time OS. We can guarantee some schedules of the tasks. It cannot delay anymore. It does not delay anymore, so that we can have, we can expect what's going on in the future. So that's the most important part of real-time OS. So there are many real-time OSs that we can choose, Linux-based and QNX and Windows-based. In our case, we are based upon Ubuntu, which is Linux, using the Genomai kernel. This is what we are using. And this is growth-based our system integration. So here you can see that because ROS 1 does not support fully the real-time performance, so here the lower part is not using ROS directly, so we are using shared memory to communicate among threads. So there are many threads actually, kinematic threads, controller threads, IMU, FT thread, COM, computation and controller threads, etc. So we have many threads, but they are communicating through shared memory. However, we are using ROS to communicate with other part of the programs, GUI, such as GUI, avatar, like master system and other programs. So those are not supposed to be real-time. So whenever we are communicating with non-real-time programs, we are using ROS. However, inside we are using shared memory. However, we understand that ROS2 is currently actively being developed. So I think in the future, this part also can use ROS to communication later on. And this is our most recent development or demonstration of our robot, TOCABI. We are participating in Prize Avatar Robot Competition. So this is the practice movie when we participated semi-final in September. So we can see the robot demonstration here. Teleoperation interface. Right now, robot is controlled through teleoperation. So operator is controlling the robot, and this robot or the operator is over here. He wears some trackers and gloves and HMD, and through this interface, you can see and hear and feels what's going on the remote side. And the operator is actually interacting with the recipient on the remote side. So he can play with him and dance with him together. And these were practice for the competition last month. As I mentioned, one of the main features of our robot is the large workspace of upper body. So whenever a robot moves, it has quite similar or close motion to human upper body. So this is the end of my presentation. Thank you very much. Bye.